Yes.
Yeah, it's very interesting topic, and I'm not very familiar with it, but I'm just interested. You talk about the jet stream. I'm interested whether you can use that to do the weather forecasting, or you can just look back. Can you?
Oh no, the jet stream is key to weather forecasting. So when I look at the weather forecast, I don't look at the surface. I look at the jet stream because I want to know what the jet stream's doing out in the future, because that tells me, whether we're headed for a warm pattern or a dry pattern or a wet pattern or whatever. So the jet stream is absolutely essential to weather forecasting.
Okay.
Yes.
So you were talking about the northern hemisphere. Is there analogous phenomena being studied in the southern, and is it a similar pattern or totally different?
Yeah, that's a great question.
A corollary question to that, you said 75% of the volume of the ice is already melted.
The sea ice, yes.
So the change in the depth of the oceans is primarily a southern hemisphere phenomenon? That is, the ice is coming from the southern hemisphere?
Okay, so first of all, Antarctica is a continent.
Right.
And it does have sea ice, but most of it melts all the way back to the coastline every summer. So there is one area that keeps sea ice year-round. So part of the reason why we're seeing this rapid Arctic warming and we're not seeing rapid Antarctic warming is because of this fact that the sea ice basically disappears in the Antarctic every single summer. So there's no opportunity for that extra energy to be absorbed into the surface because that white surface has disappeared. It's already gone. So the sea ice down there is not having an impact on the upper atmosphere so much, just because of that fact that it already disappears every summer. But things are changing down in the southern hemisphere too, but in different ways and for different reasons. And in fact, we're seeing an increase in the winds of the jet stream in the southern hemisphere. We think it's mainly because of the ozone hole. So as we lose ozone in the upper atmosphere over Antarctica, that's actually causing the atmosphere to get colder. So that hill I was talking about is actually getting steeper in Antarctica, and it's causing the jet stream to get faster, and it's also contracting closer to the coast. So there's a lot of different things happening there that are really not the same at all to what's happening in the Arctic.
Thanks.
Yes?
Say that weakening polar temperature gradient, are there any other technical terms for that, or is that the technical term for that gradient? I'm not an atmospheric scientist.
Right. So really what it is a weakened height gradient. So we're actually, an atmospheric scientist would be more interested in how the height of pressure levels in the atmosphere would be changing. So it's easier to talk about temperature in a group that isn't used to thinking about heights of the atmosphere. So it's more of a height gradient change.
Okay.
Mm-hmm. Anybody else? Yes.
Apologies to those who are not atmospheric scientists in the audience. I guess I'm curious about the mechanism of the speed of propagation of waves with larger amplitudes.
Mm-hmm.
I guess I'm tending to think of that in terms of linear Rossby waves.
Right. Right. So this is a little bit getting down in the weeds, but yeah. So this is an interesting question actually, because we know that when those waves grow in wavelength, there's very clear theory that relates wavelength to the speed of those waves moving. And so the larger the wavelength, the slower they move from west to east. This question of amplitude is really poorly studied, actually, in the world of dynamics. There's no paper out there that I've been able to find that says, okay, if you increase the amplitude of the wave, leaving the wavelength the same, how does that affect the phase speed or the propagation speed? And it's because it starts to get into the nonlinear part of atmospheric dynamics. And even more messy is how you go from that to one of these blocking patterns. And that's a very nonlinear event. And you can almost think of it as a breaking wave like you'd see on a beach. It's kind of based in empirical evidence. So we see in the real atmosphere when the amplitude of those waves gets larger, they slow down. And in some cases, the wavelength also increases, but I would say that it's in the realm of dynamics that's really not very well understood. Okay? Yes?
We had chatted earlier about some of the oceanic temperatures and the increase there. And I understand greater heat being retained in the Arctic Ocean, how that is interacting with the atmosphere. And you mentioned something about the Pacific, but that's not really involved in this game necessarily, but it is involved with climate change. I just wondered if you could comment.
Yeah, that's another great question, because actually it is involved in this game, because the Pacific Ocean has kind of these different patterns of temperature change through the decades. One of them is called the Pacific Decadal Oscillation. And when we've been in a negative phase of the Pacific Decadal Oscillation for the last 10 to 15 years. And when we're in the negative phase, it tends to create an area of colder than normal water along the North American west coast, so down along the coast of BC and California, and then it extends out into the tropical Pacific. So that's a cool area. Along with that is an area of warmer than normal surface temperatures up sort of in the northwestern part of the Pacific Ocean. So if you think back to what's happening with this hill again, if you have a warm anomaly there, it's actually counteracting the effect of Arctic amplification. So it's making the hill more steep, right? Because you're warming the southern part of that hill more than the northern part. And so I think what's happening is that we don't see an increase in the waviness in the Pacific so much yet. And I think it's partly because we're having this offsetting effect of the warm water that was up in the North Pacific. But in the last year, that warm pool has shifted, and it looks like we're moving towards the positive phase or the warm phase of this oscillation. And so I think we're going to start to see the effects of Arctic amplification starting to emerge in the Pacific as well.
Any more questions?
Yeah.
Thanks for your very interesting topic. And just in my personal opinion, if we stand at the point where we right now, we look back, we can use a lot of things to explain what happened in past. But just on another side, if we just stand 2 years ago, where we experienced the ice list period in the Great Lakes, we cannot predict that 2 years later we will experience an baddest winter in the Middle East. So if 2 years ago we can we use the jet stream as a predictor to predict the climates in North America or North Hemisphere?
Sometimes when there's a thing happens like a strong El Nino or a strong La Nina, then there's a force that's affecting the jet stream that gives us some predictability. But right now, we can't say, for example, this winter is going to be like last winter or like the winter of 2012. We really can't say. But what I think is also important is that what our work is showing is that no matter what you get, it's going to stick around longer. So the persistence, I think, is something that we can predict. And so the next step is to figure out ways to figure out where those waves are going to set up in any given year. Some years it's easier than others if we have a strong thing like an El Nino, but this year not so much. So yes and no.
So I think it's a good time to thank Dr. Francis again, and if you have more questions, you can ask them out where we have refreshments set up for everyone. So let's thank Dr. Francis. And is the tradition for Water at Wayne seminars, I also want to present Dr. Francis with a guava tile produced locally.
Nice.
To enjoy when your trip home.
Thank you. Thank you very much.
And just an announcement, we do have another Water at Wayne, November 5th. John Gray from USGS, National Sediment Specialist, will talk on sedimentology and geomorphology and sinology. Oh my, that's actually in the title. Okay, so you can enjoy some refreshments outside.